Okay. In the first part of the class, we discussed about REE, the mean of the square of the end-to-end distance averaged over, it's a statistically averaged quantity, which gives you a measure of the spread of the polymer chain. In this part, what we shall discuss is the distribution of the end-to-end distance. So the mean of RNN is calculated, but it is possible that some values of the end-to-end distance could have a higher probability compared to others. Like suppose so a fully stretched chain, which would have a end-to-end distance of n into b, right? So that end-to-end distance, we'll see that has a very low probability, whereas a more coiled conformation is a higher probability. So we are now not only looking at the mean, but the distribution of this end-to-end distance, right? To discuss that, we shall basically map the polymer conformations of so the different polymer conformations to a random walk in 3D. So basically each step of the random walk, suppose equal to b is basically the bond length, you can take that, and that is equivalent to one step of a random walk. So basically you have a random walk in 3D, you can take a step in any direction in the 3D space, but each step is of length b. You can choose just b equal to 1, and that is equivalent to the subsequent bond vectors along the polymer chain. So bond vectors along the contour of the polymer chain, I plus 1, I plus 2, to be basically pointing along any random direction. And so each bond vector, so n bond vectors corresponds to n steps of a random walk in 3D, right? But we shall first consider a random walk in 1D, and that will work out the statistics for that, and then extend it to 3D. So what are we after? So we are after WNX, and that is the number of trajectories with n steps or equivalently polymer bonds, such that the net displacement is x. So for a particular net displacement x, or a particular end-to-end distance, you can have various kinds of random walks with the same displacement x, or various conformations, the same end-to-end vector REE or RN actually, which is corresponds to one particular end-to-end vector. And we want to find out the number of trajectories, or rather number of conformations, which corresponds to a particular value of x, or equivalently a particular value of end-to-end vector. Now let's consider this in 1D. Now remember, we are considering an ideal polymer chain. So basically monomers can sit on top of each other. So basically you could have Ri in one direction and the Ri plus 1 exactly opposite that of minus Ri. So monomers can basically sit on top of each other. There's nothing which prevents uh, basically two monomers on coming on top, sitting on top of each other, and so we have an ideal polymer chain or a random walk in 1D. So suppose discussing about a 1D random walk, suppose you have n plus steps in the positive x direction and n minus steps in the minus x direction. Suppose plus x direction is to the right and minus x direction is to the left. So you have n plus steps to the right and n minus steps to the left, and the difference between n plus and n minus will give you the net displacement, which is x. And of course you have total number of steps equal to n, so n plus, and if you add n minus to n plus, so you will get n. Okay. And what do we want to calculate? The number of ways with n steps that you end up with displacement x. To give a to make this question more concrete, suppose you have a n step random walk, n equal to 4, and suppose displacement equal to 0. As a consequence, you need to have 2 steps to the right and 2 steps to the left. And here I show that there are 4 ways, 4 different random walks which you can have with 4 total steps and net displacement equal to 0. And so basically this points the number of steps taken, or time if you like, and you can have a step to the right and a step to the right and a step to the left and a step to the left. That's one random walk. And you could have right left and then right left, and that's another random walk, and each has a displacement of 0. Or you could take 2 steps to the left and then 2 steps to the right. That's an independent random walk. And then right left left right, and that's another random walk. So then total number of ways, we're talking of polymers, the total number of conformations that you can have with 4 bonds, right, and 0 net displacement is 4. So 4 different conformations or 4 different random walks. Just to give another example, suppose you have 4 steps but net displacement equal to 2. Then you need to have n plus the number of steps to the right to be 3 and number of steps to the left to be 1. And again, you can work out that you have 4 ways or 4 different random walks which corresponds to a displacement of 2. So for example, right, and then 1 left. Net displacement of 2 and a possible random walk with this particular displacement and n equal to 4. Or right, left, right. So this is another way. And similarly, you can have right, left, right, right. And this has a net displacement of 2, and this is another random walk. And so on and so forth. You can try out the last one. Okay. So what is the question? So the question we are asking is, in general, if you have n plus number of positive steps or steps to the right and n minus negative steps or steps to the left, right? How many random walks can you have? Total number of steps fixed, and number of steps to the right fixed, and number of steps to the left fixed. So what you could do is consider n plus to right steps to be object of kind A and n minus to be object of kind B. And the equivalent question is, in how many ways can you arrange A plus B objects in a line where A is considered indistinguishable and B is considered indistinguishable, and in how many ways can you arrange it, right? So I've written that basically B objects corresponds to left steps, and they are all identical. You can't distinguish a left step. So in how many ways can you arrange it? In this it's a permutation combination problem, and the number of ways you can do it is n plus n minus factorial. And then since you can't distinguish between A and B, you can so basically it's then divided by n plus factorial, and similarly you can distinguish between n minus steps or B objects and n minus factorial. There's a certain number of ways that you can do it, right? And so for a particular displacement, this is the number of random walks can you have for a certain displacement, where n plus plus n minus equal to n and n plus minus n minus equal to x. As a consequence, you can solve for n plus and n minus and put it back in this equation, and what you get is n plus n plus x by 2, which is n plus, and n minus x by 2. And of course, n plus and this numerator is just n factorial. And this is the total number of random walks possible for any one particular value of net displacement x, uh, right? Where the total number of steps is n. But remember, here we have fixed, so Wnx is for a fixed displacement, but the total number of walks which are possible, the total number of walks which is possible for any value of x is 2 to the power n, because each step you can take either to the right or to the left. Similarly, the next step you can have take to the right or to the left. So the total number of walks possible for n with n steps without any criteria or any constraint in the value of x is 2 to the power n. So Wnx is a subset of the 2 to the power n different random walks possible when you have constrained the net displacement to be x. So for certain values of displacement x, Wnx will be more with fixed n steps. Remember, all to the 2 to the power n walks, random walks, are equally likely. Right? All walks are equally likely, but some values of displacement are more likely than the others. So all walks are equally likely, but some values of displacement are more likely than others, and those values of displacements are more likely than others for which Wnx is more. If for certain values of x, you have a larger values of random walks possible, so those values of displacements are more likely to occur compared to a displacement for which Wnx is less. Of course, this Wx corresponds to the end to end distance in 1D, right? And the corresponding language will be that for a certain value of end-to-end distance, the number of random walks on conformations are more likely than the others, and thus we can calculate which values of x, right, or which values of REE are more likely than others, and that calculation essentially gives you the distribution of REE, right? So our aim is to find Px in the random walk language or the distribution of REE in the polymer physics language. Okay, so what is the probability to have n steps and the displacement of x? It's essentially equal to the number of random walks corresponding to x divided by the total number of random walks, right? And that's what I've written here, where Wnx, as I've shown in the previous slide, is n factorial upon n plus x by 2 factorial, solving for n plus and n minus, and n minus x by 2 factorial. And now this Wnx, when n is extremely large, using the so-called Stirling approximation, which has already been introduced in a statistical physics class, valid for large n, log n factorial. For large values of n, one can write log n factorial, right? So basically you have to take log Wnx, then log n factorial. So log n factorial can be written as n log n minus n. We're going to do all of this and do some algebra, which I actually once also worked out in the statistical physics course. And for the third year students, the algebra, it's just a series of around 10 steps. Can be found on page 67, section 2.5 of the polymer physics book. Rubinstein and Colby, and you can show that this quantity, or rather P and X, can be written as basically this quantity by this. You take some log into some algebra, can be written as a Gaussian. Okay, so this is a Gaussian function with a peak at the center at x equal to 0, and you would know that this would be the variance. If this is the Gaussian function, then this has to be the variance, right? Now, the catch is, if you notice, that if n, the total number of steps, is even, then the next displacement, okay, in units of B, cannot have values such as 1, 3, 5, and so on and so forth. Why? Because if n is even, then either n plus and n minus both have to be even, and if you subtract the two, the net displacement has to be even. Or if n is even, you can also have n plus to be odd and n minus to be odd, but again, when you subtract the two, you cannot have the difference in the two values cannot be odd. Similarly, if n is odd, x cannot have values such as 2, 4, 6, 8, right? Because one of the two, n plus has to be even and n minus has to be odd, or vice versa. So the difference all necessarily has to be odd. So effectively, if you have a random walk, a very large number of steps, okay, and you ask that suppose the random walk ends between some value, suppose a and a plus dA, which corresponds to different values of x. So some values of x are odd, correspond to odd number of steps, and or some values of x correspond to even number of steps, right? Then basically, so to have a particular value of x, you can either have an odd number of steps or an even number of steps, and the probability is half. So p and x, depending upon whether you have an even number, total number of steps, or odd total number of steps, is actually half of this previous number, which can be written as 1 upon, basically 1 upon oh, so it essentially can be written as 1 upon root 2 pi n to the Gaussian function, right? And x square average, so basically x square into p n x minus infinity to plus infinity, since it's a Gaussian function, can be shown to be n. This is the variance, which we most probably already know from your kinetic theory of gases or some other lecture, properties of the Gaussian function, right? And how does one calculate that? Well, one uses the properties of the gamma function, and here I have already worked it out. 2 equal to 2 into 0 equal to infinity x square into this quantity, right? And this prefactor is also here, and I've shown that x square average by using properties of the gamma function to be x, which is an x square average is the variance. So basically we can write P1D nx equal to this quantity, where we have replaced n by the variance and here by the variance, and x squared, yeah, so basically this is something like the mean end-to-end distance. Now in 3D, now this was calculated in 1D. Once we want to get to 3D, where so in 1D each step was of length 1 or length b, but if you want to consider a random walk in 3D, remember that each random step or each bond is bond vector of length 1, right, or length b, uh, can point in any direction in space. So for the 1D random walk, x square average was equal to b into n, or rather each step was in of length b. But now this length, this vector, this random vector, bond vector, will be in 3D, right? So what we are asking is the probability in 3D with n steps such that the end-to-end distance, or the end-to-end distance or the random walk in 3D in n steps ends up between Rx plus drx, ry plus dry, and in the third direction rz plus 3rz. So Rx is the net displacement in the x direction due to n steps, right? So one needs actually to calculate Rx square average instead of x square average, Ry square average instead of y square average if there was a random walk in 1D and along the y direction, and so on so forth, right? So in this one, so this is the probability. So a similar function where x square and this x square has been replaced by Rx square. It's the net displacement in x direction in 3D at the end of n steps, right? So it will be something like this, but the probability in 1D, in the y direction, in the z direction, and this is the probability. Now one knows that the R square average will be NB square, because each vector, each length, each step was length b, and this is what we have calculated in the previous case when we were calculating this quantity. And any direction should have equal weightage, so that should be Rx square plus Ry square plus Rz square, and since it's equal weightage, it can be written as 3Rx square, so that Rx square equal to, see, R square equal to NB square, which we have shown in the previous section, equal to 3Rx square. So Rx square will be NB square by 3, which is also equal to Ry square equal to Rz square, which, since all three directions are equivalent, right? So the P1D random walk in X is going to be replaced by 1D n steps net displacement of Rx, right? And that is going to look like 1 upon root 2 pi Rx square, right? So there was x square, now it is Rx square, net displacement in the x direction with a certain value. So this is a Gaussian function, right? And Rx square can be replaced by NB square by 3, so you have a 3 coming here, right? Now in 3D, n with R vector, right, for a certain value of Rx, a certain value of Ry, and a certain value of Rz, such that the end-to-end vector ends between Rx and Rx plus dx, Ry and Ry plus dry, and so on and so forth, would be basically the product of the three vectors, right? And here, so basically you see this is a Gaussian. I've just made the product of the three independent directions, right? And since this is a Gaussian function, you would say, okay, there's a Gaussian chain model as well. And note that this has been a vector. Now, if you integrate over all directions, over theta and phi, right? This was in a certain unit volume of space. But now suppose you convert to the spherical coordinates and integrate over all theta and phi, so that you ask what is the probability, and I've given a star here because this is a vector and here now this is a scalar, that the end vector, the polymer vector, end-to-end vector, ends up between r and r plus dr, independent of the direction. You have integrated over theta and phi. Then what you get is basically this extra 4 pi into r squared term. And this is r square, right? This was rx square plus r by square, but this has been spherical polar coordinates. This is r square, right? Vector lies between r and r plus dr, any direction. Now, what is this function? This is r square into e to the power r square. You have seen such a function by, of course, variance. And you have seen such a function in the Maxwell-Boltzmann distribution, right? What is the probability that the speed is between v and v plus dv? And there again, it was a Gaussian. And again, when you take a scalar, it becomes basically, so I have written down explicitly the Maxwell-Boltzmann speed distribution. You can compare with this with this, and you have 4 pi, and you have this prefactor to the power 3 by 2 into v square, and here you have r square, and e to the power minus mv square by 2 kbt. So you know how this function looks like, right? So it looks like the Maxwell-Boltzmann distribution. It rises up, has a peak, and gradually falls to 0, and it's not symmetric, right? And the total displacement, the probability with the total displacement is 0, or the v is 0, is 0. Now, if you compare these two expressions, you can see that you can put kbt by m equal to nb square by 3. You have to just compare. So basically, you're writing down in terms of variance. Here, the variance is nb square by 3. And here, basically, it is kbt by m, right? V square is speed. It's a scalar quantity. And so this can be compared. And if you know that, then you can say that the peak of the distribution, if you remember your kinetic theory of gases, was at 2 kbt by m. And correspondingly, the value of end-to-end distance for which this distribution will be the maximum will be 2 nb square by 3. Right? Also, the mean square velocity, mean square velocity, or mean square speed, if you like, because you're taking a square anyway, so that's a scalar quantity, was 3 kbt by m, and now that comes out to be 3 nb square by 3, that is equal to nb square, and that is end-to-end distance square and mean of the square. And this is what we also find out. So basically, I've calculated the distribution, which gives the right moments, right? So you see again a use of the Maxwell-Boltzmann distribution. Before I end this lecture, let me emphasize that this was carried out for an ideal chain, no excluded volume interactions. And in the ideal chain, the end-to-end distance came out to be n to the power half b, and we also calculated the distribution. For a real chain where you incorporate excluded volume interaction so that two monomers cannot sit on top of each other, chains cannot cross each other, as a consequence, the end-to-end distance, as we shall see after 2 classes, shall be goes as n to the power 3 by 5 into b. So this exponent increases from 0.5 to 0.6, right? And you might think, but that's very small, and it's an exponent, and it just changes a bit. But suppose n was 1 million. Please calculate. So square root of 1 million is 1000, right? Trivial. So you know that the end-to-end distance in this case, for a chain with 1 million, will be 1000. But this small change in the value of the exponent n to the power 3 by 5, calculate 1 million to the power 0.6, and you'll get some value around 4000, which is 4 times the end to end, the spread is 4 times the spread of the ideal chain, and then that's considerable. And if you take the volume, the so-called pervaded volume, the approximate volume, so the chain is taking all possible conformations, right, in space, or sometimes it's pointing in this direction, and sometimes in this direction. If you take an approximate estimate of the volume that this chain occupies, it's a dilute solution, it's not interacting with other polymer chains. Then this real chain, because its end-to-end distance is its approximate spread is 4 times that of an ideal chain, is actually 64 times more. The volume spanned, estimate of the volume spanned by this polymer, is 64 times that of an ideal chain. Yes, so we shall need to discuss real chain as well, but we have to wait for a few classes. Meanwhile, just to emphasize that this ideal chain is also called the freely jointed chain model, right? And if you consider that this bond length is going to tending towards zero, but in a way that the total length of the chain remains constant, is basically you continue make the function, the contour length, a continuous function, then it's the so-called Gaussian polymer model. And for each AREE goes as n to the power half by, into B. Okay, so that's it. So we'll meet next class. Thanks.